Okay, so the title that I gave my talk was Fire Data, How Big is Big? And not so descriptive, but the reason that I sort of landed on this was there's a few things that have been going on that I've noticed is, one is that I love, firstly that there's a big uptake in the industry with the fire standard. So definitely in the past few years, the growth and the community has sort of been amazing in that regard. The next one is, there is now starting to be quite a big uptake in the amount of fire data being produced, right? And with that, we need to keep up with, I guess, storing that data, both now and sort of well into the future. So, certainly we haven't seen any slowdown. And, people then with these sort of things in mind come to us and they're like, hey, we need to store a lot of health data or, a lot of fire data or whatever the question is. And the next question I think I would ask back is, well, how big is big? Like, what is big to you? And there seems to be, from what I've noticed, like fairly defined, I guess, categories of, there's a lot of businesses and health orgs that are, maybe big to them is kind of on the lower end of the scale, especially when it's in cloud. But things can definitely sort of ramp up quickly. And we're also like looking at, supporting people through the growth of their company and their products and their businesses, sort of well into the future. So I'm going to keep going on. Next. Okay, so who am I? Yep, so my name is Brendan. I'm a software engineering manager at Microsoft. The products that I work on day to day, so the OSS FHIR server for Azure. So that's the open source code that we have in GitHub. Anyone can download it. You can spin it up in your own Azure subscription. No limits, see exactly what's there, the way that we've implemented everything in .NET. We also have two managed products. So Azure API for FHIR. So that's backed by Cosmos DB, which is the cloud scale document store. And sort of the latter addition to our product family is Health Data Services, which is kind of like a workspace model. So in here, you can provision a FHIR service, which is backed by SQL Server. And you can also add in, IOMT connectors, DICOM services. So it's kind of like bringing the whole like workspace model together to, operate on health data. Okay, so the agenda that I had for today. So you might take today as kind of sort of like, my learnings and observations over the past few years of working with FHIR. Hopefully I can, throw a bit of a light and maybe a different angle on some of the, I guess, patterns and observations that I've had. So the first one, and I think this is not too dissimilar to, the things that have already been talked about today. So, how the different types of access patterns can influence your storage solution. So I will drill into that. How things change as data volume grows. So, that's the question, like, how big is big to you and how can we support your growth? And sort of, looking to the future where, I think I'll try to summarize the patterns that I see, to, put my vision, I guess, forward, based on what I know to what sort of more cloud-based native solutions might look like. All right, so I'm using the well-known pillars here. So data access patterns definitely falling into these two categories. So online transaction processing, and I think this is the CAP theorem that's already been discussed today. Not in exactly the right words here, but I think that's pretty much what I've listed. So throughput and latency is important, consistency is important, and availability is important. It may not be all at the same time, but mostly what I hear is that, yes, when we have an online transaction processing REST API, we want all of them as much as possible. The other category, OLAP, so things like analytics, population level queries. In general, latency might not be as important just because of the type of work that you're doing. And these types of things, will then sort of feed, later on into, analytics or machine learning pipelines. So I'm going to drill into this a little bit more. So what uses the OLTP? Primarily, I would say this solution is the FHIR REST APIs. And there's a bunch of applications that sort of fit into this. So applications using smart health information exchanges, silos and aggregators can use this. Should have put an asterisk there. Patient data access APIs, provider directories, kind of the list goes on. So, anytime you are looking for that, online REST API, this by design is your go-to. And then I thought I'd list some of the query patterns. So things that I've noticed, that perform in general well. And in this one, I did put some asterisks because I think this is an important consideration that in general, no matter what the backing data store is, reads are always fast. Like we always know how to get to a record if you knew the ID. So in this case, if it was patient 123, it doesn't matter if that patient was in Cosmos DB or if it was in SQL Server. We always know how to get it, in the minimum possible time. The next one I put pages with the star, so pagination. And I think, we've already mentioned today that at some point, pagination does put some strain on, certain, I guess, data stores. So SQL may eventually have this problem. But what I've noticed with document-based data stores is they, in general, kind of like shard and partition sort of under the covers. So the way that they work in their continuation tokens is they're, basically like moving their ranges forward. So they may not always hit the first partition. And as you kind of move through, they're kind of like looking in, different partitions and therefore kind of like spreading the load out. If you had this case, in this example here, where a patient where the name is Smith, it may not have to try very hard before it can fill up a page of results and return it to you. Selective queries, so SQL-based systems, if this thing is in the index, then it's going to be quite fast to sort of find those results and return them to you. And I don't know if this is surprising or not, but in general, include statements do tend to perform pretty well. And I believe the reason for this is that as long as you have appropriate search criteria that returns in an okay kind of time in the initial search, the included results are generally just linking to a bunch of IDs. So in document-based data stores, we can just read them in. SQL-based data stores, it's more or less just a join based on that primary key. So they generally seem to perform pretty well. What seems to perform slower? Chain searches seems to be across the board in all data stores. And the reason, SQL, it's joins. In document-based data stores, you're kind of forced to do these sub-selects along the chain query until you can kind of like, basically apply those filters either backwards or forwards, depending on the strategy. But it is, it can be quite a lot of work. So it's something to be mindful of, but I'm not, saying that you shouldn't use them because they are incredibly useful. That's why they're in the standard. But it is a consideration. And I put selective queries here again, but this one has an asterisk. So maybe the reason that pagination works well for document-based data stores, if you were just changing data stores to fix all your problems, you may find different problems in the next data store. So for selective queries in document-based data stores, you're looking for one object in potentially billions of items. And the way that they're working is that you may be sending that query in parallel, to hundreds of petitions. So it can kind of be like an incredibly extensive amount of work just to find one thing. And in this case, the example is identifier. So it's not, it's not the primary key. So it's some search index-based thing. Conditional I put here, not because I think it's particularly problematic, but it can be problematic depending on your use case. So if you are designing your system to say, hey, I'm going to import all the backlog of my data using, conditional creates and updates, I guess just remember that conditional is a composite operation. So you're forcing a search before the next operation is applied. We definitely in FHIR, I think, have been evolving faster ways to import data. So definitely a consideration there. And again, depending on the data store, counts and sorts can be problematic. So, definitely in document-based data stores, count, you're kind of like forcing all petitions to return a result. again, it can be, quite a lot of effort. All right, so taking a breath here. So OLAP, a few different takes on this. So we can export a lot of our data from our, I guess, primary OLTP data store with export. In general, it's going to end up in, I guess, in a few different places. So either like a blob storage, a data warehouse, or a data lake. Yes. Okay. Yes. Sounds good. Okay. And then for the query patterns for these, in general, I feel like once you move to like an OLAP-based data store, you're generally not working with the REST API. So you may be looking at schemas in the OLAP data store that are either flattened or denormalized. So we may choose to sort of flatten the FHIR out into tables or denormalize it. I think I've seen some solutions transforming into things like OMOP. Or you might choose like another querying language that's designed, I guess, for FHIR, such as SQL on FHIR, Databricks, and there's sort of other hierarchical based querying languages that can be useful as well. And another querying pattern, I guess, is the export, which can be filtered, or it can be the entire population. And it matters because maybe filtered, you're looking at some particular slice that you're interested in, or some particular time segment. Entire population obviously refers to like, I want all of my data there, and it could just be updated with periodic updates. So we do have an example here that we have also in open source from Microsoft. So your SQL backed FHIR data store here, use the export command, goes into some blob storage, and then there's sort of an additional pipeline here that's going to import it into your analytics system. So I wanted to try to put some numbers, moving on to the next segment. I want to try to put some numbers behind like, what does data sizes mean, and how does that sort of affect scaling with FHIR? So I started off with like 0 to 1 terabyte. So these are all in ranges. Think of this as a journey. Perhaps in the future we'll have sort of much bigger numbers here, but in general, I don't think you can sort of escape a lot of the current computing constraints. But I think 0 to 1 terabyte, I think you have all options on the table. I think you can definitely pick your favorite, most comfortable solution. And in general, it's probably just going to work. And then I think as you sort of travel on your journey between like 1 terabyte and 10 terabytes, it's probably achievable just with scale up strategies. More cores, more disks, more CPUs, bigger VMs, all that sort of thing. And you're probably going to be able to achieve, I believe, that sort of solution, within that sort of 1 to 10 terabyte range. But I think when things start to get interesting is once you travel up from there, right? So you go from 10 to 50 terabytes. So maybe typical sources here is like a multi-source aggregation, strategy. So here, I think indexes and petitioning becomes important, because if you get it wrong, latency is now amplified. I think we just mentioned in the chat, like joins start to break, things start to become noticeable around these ranges. And also maybe cost becomes a factor. Disks, they're cheap, but they're not free. So the way that things are stored, can become important. And then we can keep traveling up. So, 50 to 100 terabytes. And this is where I think you have more, more things start to become important here as well, right? Import and export speeds are imperative. Petitioning strategies are highly important. You want to start to make sure you've got efficient cost and storage, factored in there, and operational concerns. So backup time, maintenance operations, these become important factors as well. And I just put greater than 100 terabytes because I think by this point, this strategy is probably going to keep carrying you forward, right? 100 terabytes, petabytes. Like this is where I think the strategy very much becomes, there isn't one thing big enough that will fit all of your data. You're looking at a horizontal scale out strategy. So sharding and petitioning strategies are imperative. Your import export speeds are imperative, like having a good way to do that. Transactions and consistency can be more complex, still solvable, but definitely there's more moving parts. And what you ideally want, is constant time backup store. All right, hopefully that's good. I just wanted to highlight here that depending on how you slice it, If we were, say, importing maybe 5,000 resources a second, it may be okay at some point, that we keep that speed. But once we sort of reach high data sizes, we need to sort of, look at what do we need to sort of keep the constant time. And, there's a lot of stuff that sort of comes into here. Like you might be maxing out like the log rates and disk speeds and stuff like that. So, definitely the scale out strategies are important. I wanted to bring this up just as a food for thought, is that raw JSON doesn't necessarily equal stored JSON. And the three examples I have here is, in document data stores, if they're storing JSON, there is a penalty to be paid for the indexes that are created. And it's the same in SQL, but what I've generally noticed in SQL is that with compression and the right types on indexes, where a Boolean is a bit, it's generally sort of leveled out at about 1-to-1. And I guess just as a comparison, things like blob storage are obviously going to store it verbatim. I wanted to put this in here as like a throwback to some of Graham's earlier thoughts when he was discussing, like, should you be storing FHIR in your database as like, like a JSON blob, or should it be a relational schema? And sort of looking at the spec over a few years, he's actually already, like, there's already two schemas defined. So you have the schema of the models, which is, I think, what we all naturally go to. And then you have the search parameter schema. So it redefines the names it's interested in. It redefines the relationship between other search parameters. And really, this is kind of like an extraction and normalization process. So if we took that forward, this is just a proposal, a theory of, where I think sort of cloud first, cloud native solutions sort of might get to in the future, is that, it's sort of optimized, sharded indexes sort of on the front end to sort of make searches as responsive as possible. Things are stored in blob to kind of reduce the size of the indexes. Plus you have efficient, cheap storage. And then the further thing that might do in the future, and I think this is where, things might eventually migrate, is it gives you kind of like, potentially a unified view with analytics. And even if you're sort of starting out here as like, I only want an online transactional processor, I don't need OLAP yet. At some point, you probably need OLAP. So I think sort of having that build on model is going to make a lot of sense. All right, so sorry to go a little bit over and for a couple of dropouts, but hopefully I've been able to sort of, present a couple of ideas and a couple of views on the future here. So yeah, these are the takeaways that I had. So how things change as the data volumes grow. And yeah, thank you for listening.
Thank you, Brandon. Questions for Brandon, please?
Brandon, the metrics you showed with the data load, is it for Cosmos DB or for SQL?
I've chosen some more like hypothetical numbers here, but they are ones that I think are reasonable and achievable at this point. But yeah, I've kind of given a hypothetical scenario, and I just wanted to show the relationship between loading the data in at those speeds and sort of what happens, if you have 100 terabytes of data, that we really kind of need to flip the paradigm on its head to, look more at constant time as opposed to, just waiting.
The question about partitioning and sharding, do you mean what sort of partitioning do you propose to use? Partition by patient or something else?
Maybe we could actually leave that one for the roundtable there. Okay. That's a great question, and there are so many different ways that you could slice at that. So I don't think the one answer works for everyone.
Mm-hmm. And what's the difference between when you mentioned partitioning and sharding? So what do you mean by partitioning and by sharding?
Right. So what I mean by that is that so a shard, you might say conceptualize that as a database, and partitions might exist sort of within that shard. So in the example, I guess in the chat, so maybe if you did petition by sort of like patient IDs or something like that, then you would, I guess, be able to partition your search indexes within one physical database, but you may have multiple physical databases.